a problem up on the
Yeah.
board.
What? Wait. When?
Is it that one kid that always comes in?
Oh, when? It was.
Sorry, I'm
this-
late, guys.
Yes,
Yeah.
We've been waiting for you.
We didn't see Lake Mexico? Show up where-
Chapter 11,
That's it?
No, it's not Mexico.
That's it?
talking about metals
I
today.
can't say things.
Brought the wrong book?
Both of them.
Oh, brought the wrong notebook too?
Yeah.
Where's the materials notebook?
In my office.
All right,
Wait, is this office the same?
We're not gonna wait.
No.
all right, metals and alloys. Basically just talking about what metals and alloys
Daniel.
are typically used in engineering structures. The most common metal or alloy are the ferrous alloys.
They're very even.
What is the most common?
Steel.
Iron.
There you go, steel. Thank you.
Excellent.
Steel, the most commonly used engineering material. So steel is defined as anything from 0.05 to 2.0 weight percent carbon in iron. So any iron alloy that has between 0.05 and 2 weight percent carbon, we call a steel. Okay? Within that category, we have what are called low alloy steels, which have anything less than 5 weight percent total non-carbon content. In other words, very nice. My daughter got an A on the test. So
What test?
I'm assuming though.
I haven't gotten a test in a really long time.
Yeah.
Last time I got an
Okay. So low alloy steels means we have less than 5 weight percent of all non-carbon content. So, chromium and molybdenum and manganese and whatever else we might throw in there, if it adds up to less than 5 weight percent, all those other stuff, then we call it a low alloy steel. Okay. And then obviously a high alloy steel would be the other end of the spectrum. What's the other?
Non-carbon, but also non-iron?
Right. Right. That's what I'm saying. So the alloying content, I guess I could call it non-carbon alloy content.
Oh.
So the alloy materials are typically the ones that are not the main thing. What's the other ferrous alloy that we use in significant amounts? No.
Donatite.
No.
Gold.
What is the other ferrous alloy? I'll give you a hint.
Aluminum. Aluminium.
I will give you a hint. It's not ferrous. I'll give you a hint. Your house might have a railing made from this.
Cassidy says iron.
Chrome.
Cast iron.
Cassidy
So it'd be like a stove. It's just a stove
Okay.
made out of it.
Cast iron.
Oh, not a stove.
Maybe.
That would have been good, yeah. Stove would
That's
have
not
been
even
good.
stove. It's a really common.
Cast iron.
Yeah,
Cast iron then
It's really the cast
is anything between 2 weight percent and 4.5 weight percent. Carbon. Sorry, weight percent carbon. Bless you, my son.
And bless you. And bless you. And
All right.
What about Bueller?
you don't get that.
Ferris Bueller?
No. Different
He
spelling.
took-
I'm
He
sorry.
took the day off.
That's different.
So these are the two, ferrous alloys are the biggest chunk. The low alloy steels are the most common. So either the plain carbon steel would obviously be just carbon and iron and nothing else. or the low alloy are the most common because they're least expensive. Right? If I got to keep putting more alloying elements in there, it's going to make it more expensive. The steel is cheap, chromium not so much.
So what else is in chromium?
Chromium is an element.
Oh.
Cr. Maybe we should take chemistry. Oh wait, you're taking chemistry! Okay, anyway.
To be fair, I didn't know that either.
I was thinking like
It's not allowed.
chrome rims on a car.
Right, they coat steel with chromium.
Okay.
I mean, not anymore, I mean now. I'm sure that there's
Something else.
other stuff involved nowadays, but that's where the chrome came from. All right. Plain carbon steel, the most common ones. So, we have two different designations. We have the AISI, the American Iron and Steel Institute designation. Yeah.
At least it's not nice.
Or the SAE. Anybody know what SAE is?
Systematic.
Britain.
Rate.
You should know what SAE is.
Probably has something to do with
Say
electricity.
something.
Nope, it has to do with where you work this summer. Society of Automotive
Speak
Engineers.
up, speak up.
She had it. She had it.
Is there like a
Ideas.
5W20 after it, or?
Wait, is that like?
Society of Automotive Engineers.
Is that like
There's two different ways of designating materials, okay?
I think
So,
it means air.
the general consensus is you use XXYY format. The XX is the alloy type. The YY is the percent carbon. And it's done in 0.YY%.
Can you say what
And-
plain?
Go ahead.
Can you say what plain carbon is again?
What plain carbon is?
Yeah, like I
Just carbon is an iron, nothing else.
And then low alloy has other.
Carbon, steel, carbon, iron, and maybe some chromium, magnesium, molybdenum, whatever.
Okay.
Okay. Does that make sense?
So plain carbon is basically quote unquote pure steel almost. It's just
Right.
iron.
Right. Well, anything with carbon and iron within these concentrations is considered steel.
Okay.
Okay. But plain carbon steel is just, so the alloy type for plain carbon steel, for instance, is 10. Pretty sure I didn't write that down, that's interesting. Huh. I didn't write it down.
What does alloy type mean? Like the
Meaning-
element?
Meaning, no, there are, I'm gonna see if they've got the tables in here or not. Meaning, yeah, what combination of elements? So 43 here, yeah, okay, so 10 is just plain carbon steel.
Wow.
11 is resulfurized steel. 12 is resulfurized and rephosphorized steel.
So like it's something you have to look up in the tables.
What's that? So yeah, there's nothing to know, there's no nothing quantitative, it's just a sequential list of.
Because if it was like
up to
CR,
100
if
different.
it was like CR.
No. It's just two numbers that correlate. And then, so for instance, if I told you have 1080 steel, you know that it's a plain carbon steel with 0.8 weight% carbon. What is a 1080 steel? What would we call a 1080 steel?
It's Friday.
What would we call a 1080 steel? Anybody? We'd probably call it a eutectoid steel.
Oh.
Because the eutectoid composition is 0.77 weight% carbon. So 1080 steel would be a eutectoid steel.
So what do you
Actually,
do?
1077 would be the eutectoid steel, but 1080s would actually, yes.
What would not be a eutectoid steel?
1040 steel,
1041.
right? So it's a 1040 would be a hypo-eutectoid steel, yes.
What do you do if you have a steel?
If you have something over 1%, you'll add an extra digit. So 1.5 weight% carbon, we had 10, 150.
Or 10 is, means it's just carbon.
10 means it's just carbon, just plain carbon.
What kind of steel is the best steel to make a sword out of?
All right, moving on.
No, really, Google it. It's classes.
There's not a best, there's not a best. You want to make it out of a stainless steel. We haven't talked about stainless steels yet. Okay?
What does
How
the
do you
samurai
make
make
steel?
out of?
Come on, guys. Let me finish this. It's gonna be 100 seconds.
Extremely rare.
All right. One other kind of low alloy steel that kind of gets a special designation is as HSLA steels. High strength low alloy steels. So there are ways that are, there are these proprietary compositions in which you're able to achieve very high strengths without putting in all kinds of extra alloying constituents. So, but they're proprietary.
How do you own?
A formulation? Well,
Does
I
that
mean,
mean, does that mean I can't make it and sell it? But if I had the equipment, I could still make it for my
Right.
purposes?
right, that's what it means.
Huh.
So, it's proprietary. In other words, the
Copyright.
specific composition, I mean, someone could go in and reverse engineer the material and find out exactly what composition it is. But, and actually I think you could sell it as long as they don't patent it. If they patent the composition, then you can't sell it. But then they'd have to tell you what's in it. Proprietary means they have a certain mixture and a certain way of getting it and stuff, so
They don't tell you what.
they don't tell you what it is. It's some mixture of, you know. So for instance, you might have something that says it's 0.2 weight% carbon plus some combination of magnesium, phosphorus, what else do I have in here? Silicon, chromium, nickel, or molybdenum.
That's an ore, not
That's an ore. And some combination of those sorts of things. And it may be something else, or maybe something else in there. But the point is, in order to achieve the high strength, you have to have just the right combination. It's literally, I mean, it's like, they're like cooks in the kitchen, you know, metallurgists kind of trying to come up with just the right combination. Alchemists, right.
So, but all of those still have to be less than 5 weight%.
Right, the total adds up to less than 5 weight%, the total of everything on the right. Okay.
And the reason we would want to do low alloy is just because it's cheaper.
It's cheaper to make, right, you don't have to put extra stuff in it.
So there's plenty of metals days on it trying to find this.
Yeah, I mean, a lot of the stuff's been done, right? I mean, people have been playing with metals for years. Usually, the reason they start playing with it to do something different is because something we thought was great suddenly experiences some kind of an issue. You know, in some weird environment, you know, in a nuclear power plant, this high-strength low-alloy steel suddenly starts to corrode, you know, exponentially fast, because we didn't think to test it in the presence of alpha particles, right? Which basically helium nuclei, right? So it's being bombarded with alpha particles, and all of a sudden it corrodes fast. So now we go back and we try to reinvent the steel.
Reinvent the wheel.
Hit the wheel.
Okay, so that's the low alloy steels.
Keep on beating it.
The high alloy steels are then those that have more than 5 weight%. And these are typically the stainless steels, tool steels. Right, so you want super high hardness because you're using them for tooling. Or what we call super alloys. So, this is the common, right? The plain carbon and low alloy steels over here are fairly common use. The stainless steels also fairly common use, so we have actual structure for doing things. We can't do HSLA steels because they're proprietary. They don't have an AISI or SAE kind of designation because they're proprietary. Yes.
Stainless steel act like, I used to think that those was like stainless, like it wouldn't get stained. Does it resist that at all?
Why do you skip ahead? Let me finish.
Okay.
Yes. What do you got, Brady?
Would carbide be a high alloy steel?
Carbide. So like
I know it has like tungsten.
Iron carbide,
Yeah.
so or tungsten carbide, because tungsten, and some of the carbides are not ferrous material. So tungsten carbide is a mixture of tungsten and carbon, which is coated on the end of a tool steel.
Yeah.
And so the cutting surface is not necessarily always, but then there's iron carbide cutting surface. So what you do is but again, typically it's not the whole thing, right? The whole blade is made of some kind of low alloy steel, and then there's a carbide piece that would be a high alloy steel, which would be used for the cutting purpose. All right, so stainless steels, that's where we are. What makes it stainless is typically anywhere from 4 to 10 weight percent chromium or more. So stainless steel, there's two broad categories of stainless steel. Austenitic, and do I have ferritic? Yes, ferritic. So we have austenitic stainless steel. That is, it's room temperature stabilized gamma. These are stabilized by the addition of nickel. So you put nickel in an austenitic steel, and it stabilizes the austenitic or the FCC structure at room temperature. And the designation that's used for these is either 2XX or 3XX. The 200 and 300 steels are austenitic stainless steels. So, just to give you a couple examples, 304 stainless has 18 to 20 weight percent chromium, 1% silicon, 8 to 10.5% nickel, 2% magnesium, 0.08% carbon.
What does that have to do, 3 or 4?
That's that particular combination.
Oh, okay, so there's no.
the XX don't have any particular, they're just, again, sequential. The XX here is sequential, just like the XX are over here. They're just different numbers. They don't have a numerical quantitative representation. Okay. 304 stainless.
It's not a chromium.
And then there's 316 stainless, which has 16 to 18% chromium, so a little bit less chromium. Let's see here, same silicon. It's 10 to 14% nickel, so we have more nickel. Same magnesium, same carbon, and 2 to 3% moly. So 304 stainless is something you might just see, in some kind of a tool, some kind of a piece of equipment, something. 316 is something you're more likely to see in a prosthetic device. And so the FDA approves 316 stainless, but not 304 for implanting in the body.
Just a way it like reacts with.
Right. So if it's lower chromium content, you basically, one of the biggest issues with stainless steel in the body is the leaching of heavy metals. Right? The chromium leaches out, the nickel leaches out, these other metals leach out, and you get what they call metallosis, I think. They get these extra little bits, because as the pieces rub, you get a little, just very fine powder, but it's not elemental. So it's not dissolved, it's powder. But it gets into your bloodstream and then can form pockets, and your body reacts. And
Like you pulls it out of you.
What's that?
Is it like you pulls it out of you?
Yeah, that's right, exactly. And then you'll also see 316L, which is just 316 but it has less than 0.03 weight% carbon. So 316L is low carbon 316. That's what the L means. It's 316 with low carbon. So those are the best. The austenitic stainless steels are the best, typically the best stainless steels. But if you have austenitic, then what else am I going to have? Skipping ahead.
Just cyanolytic.
Ferritic, thank you. At least somebody's paying.
I didn't say a
Somebody's
word.
probably saying.
They said there's not.
That doesn't mean it's my fault.
It's probably also.
Ferritic stainless steel, so it's alpha, right, which is normally stable at room temperature anyway. Right? So alpha, because it has lower nickel content. So it makes the alpha, or the BCC form, stable at room temperature. So examples here would be I'm not going to go through the whole 405 or 430 stainless. They have lower nickel content. As a result, they're lower cost. They're cheaper to make, but they're also not as corrosion resistant as 300. So you never put a 405 in your body.
So ferritic had 4XX for their numbers.
Not necessarily.
Not necessarily.
Because the third category then, and I'll do it down here. See if I can get this. Would be, as Joel pointed out, martensitic. And those are, let's see what numbers, 410 and 501 are both martensitic stainless steels. So use that for your knives, your razors, your things that need to have a sharp edge. As I said before, martensite's a high strength material, so you want your edge to be sharp and stay sharp. You want to make it out of martensite.
Like swords.
Like swords. Except really, you typically don't, sword's not all just about the sharp edge. Right.
It's about
You don't want it to be brittle.
Right, you don't want it to be brittle, you don't want the short.
You want it to be dull.
Just be hard, but anyway. Okay.
You gotta pick the right focusing crystal.
Okay, are we good? Yeah. All right, so those are the stainless steels, then the tool steels, also within the high alloy content, right? The tool steels. The purpose of a tool steel is to maintain high hardness at high temperature. Right? When I'm cutting something, in the machine shop, I'm cutting something on a lathe, I'm generating tremendous temperature increase, right, because of friction. So the whole point of a tool steel is high hardness at high temperature. And you generally want easier heat treatments. Right, because I can do that with 1080 steel. Right, I can just take plain 1080 steel and get high hardness. But I've got to be able to quench that thing rapidly in order to get down to the bainite or the martensitic transformations. Right? And that's hard to do with a big chunk of something. Yes?
Is tool steel as hard at room temperatures as at high temperatures?
Yeah, it's just that it maintains its hardness.
Yeah, no, I wasn't sure if there was any.
So I don't know exactly what the relative hardnesses are. But molybdenum, tungsten, and chromium are typically the alloy elements there. And then the third category, superalloys. Superalloys are defined by having high strength at very high temperatures. By very high temperatures, I mean like 1,000 C or more. So superalloys are used in things like jet turbine engines. Oh, yes.
So whenever people are like casting, remember you have a bunch of like molten metal, and it's sitting in this big metal tub thing.
Typically a ceramic type thing.
Oh.
Yeah.
Because I was curious, like how you cast something like that, if it's made.
Right,
Just
right, right.
cast things.
Yeah, so no, usually it's a ceramic.
What kind of ceramic?
You know, I don't know what specifically they use for steel, but ceramic has a much higher melt temperature. So you can chemically, right, you can cement, for instance, is a ceramic, right? So you can have a chemical reaction, make a ceramic pot, or a cement pot, and then pour molten steel inside the cement pot.
How much do you have to get cement for it?
I don't know. Okay. Are we good with the steels?
Does metal ever burn?
No.
No.
You two are like debating this existence.
Like always? No.
Stop. Okay, are we ready to move on? Answer is yes, we're ready to move on.
Yes, we're ready to learn.
Elements first.
Move on.
Okay, we're gonna go back to cast iron now, because that covers all the steels. Let's now revisit cast iron.
I don't have any way anymore.
So I haven't even gotten out of the ferrous alloys yet. Okay, again, as a reminder, that's between 2 and 4.5 weight% carbon. And up to some, depending on what you need, 3 weight% silicon. The silicon facilitates the formation of graphite. Okay, remember I told you in the iron-carbon phase diagram, I said, unless we go really slow, what's the right-hand side? Cementite, right? Fe3C. But if I throw a little silicon in there, I can cause graphite to be the second phase, not Fe3C. At least to some extent. What's that?
Graphite is what we use in our pencils, right?
That's correct. So there's two broad categories of cast iron. There's white cast iron, which is very brittle and has a high Fe3C content. There's gray cast iron, in which it's still brittle, but now because we've included the silicon, we form graphite. That's why it's called gray cast iron, because the gray graphite shows up in the middle, especially if you break it. The fracture surface looks more gray than white.
So white cast iron is actually white?
It appears white. I mean, it looks metallic when I crack it, right? It's shiny. And so it's white. Whereas the gray cast iron, imagine taking that shiny thing and then sprinkling it with graphite dust, it would look gray. So the gray cast iron, when you break it, looks gray. Yes.
So does what cast iron not have silicon in it?
It does not have enough silicon to cause it to form graphite.
Okay, alright.
And then the third category, or another category, is what's called ductile cast iron, which is basically just gray cast iron with 0.05 weight% manganese. Magnesium. M is magnesium. Anyway, Mg. And so what it does is this addition makes the graphite spheroidal. Oh. So what does graphite want to be?
Sheets.
Sheets, right? Right, that's the hexagonal structure, right? The plates of graphite. So if you have plates of graphite, it inhibits dislocation motion, right? Like we talked about with the bainite. You get these randomly oriented plates, it's a problem. But if I make the graphite spheroidal, that plate that would be blocking a whole bunch of dislocations from propagating now just became a sphere this small. Now the dislocations can propagate around. And a sphere is the least obtrusive obstacle. A plate is a much more obtrusive obstacle.
And
What's
that's,
that?
Do we want dislocations to propagate?
If we want it to be ductile, yes.
Oh, okay, okay.
Right? If we want to, if we don't, then it's brittle.
Okay.
But if we want it to be ductile, then we have to add a little
are those
mg to get it to.
those spheres buckyballs, or are they like?
No,
orange?
no, they're just spheres. They're just nothing as elegant as that. And then there's another thing called malleable cast iron, which is we heat treat white cast iron. To form the graphite nodules. Or spheres, whatever. So the idea there is it's primarily Fe3C, but we can heat treat it. You know, get it up there, let it sit at temperature so that the Fe3C can achieve its true equilibrium form, which is graphite, and it'll do it in sort of a nodule effect. So ductile cast iron compared to gray cast iron has 2 times the strength, but 20 times the ductility
Compared to gray.
compared to gray. Okay. Good? All right then. That's it for iron. But iron's not the only thing. We also have non-ferrous alloys. What do you think is the most common non-ferrous alloy?
Aluminum.
Aluminum. Get your chance, man. So, aluminum. Why do you think it's aluminum?
Because it's everywhere.
Right,
It
it's
also
actually-
doesn't
We
corrode.
literally learned from,
It corrodes, it just doesn't keep copper to the
Right.
It used to actually be pretty rare.
What's that?
I think like back in the 1800s, before they
Well,
discovered
but we're
a
not
lot of
in
it, it was like really rare.
Salt was also rare.
But aluminum is, the main advantages of aluminum are corrosion resistance and low density.
Yeah.
Right, so it's lightweight. So it's FCC, so it can be formed easily, right? It's very ductile. Low density and corrosion resistant. Okay. Aluminum alloys are named in a YXXX format. Y is the alloying component. So 1 is none, there's no alloy, it's pure aluminum. 2 is copper. 3 is Oh, no, I don't have 3. I didn't write down all of them. 4 is silicon. 6 is magnesium plus silicon, and so on.
What's 7? Do you know?
What's that?
What's 7? Just one thing.
I don't know. I didn't write down 7. I don't know if you'll look. Oh, look at you. Yeah, imagine that this stuff is actually in the book. Okay. Anyway, so one of the ones that you're most likely to work with. I don't know if there's a 3.
3 is an N.
Manganese.
3 is an N.
Yeah, I'm just listing the ones that you're more likely to encounter.
8 is other elements.
7 is, what was 7?
Zinc. And
Okay.
5
So
is...
the ones that you're most likely to encounter, the ones that you come across most are 2s and 6s. So 2024 is it a common aircraft aluminum?
6061 there.
6061, right?
And 70,
775?
77.
Okay.
That's what you're doing in South.
All right. So anyway, and they have a wide variety of properties, but and then this part is just sequential. It doesn't have the same kind of meaning. Again, there's no quantitative meaning for the XXX means. But there are a number of tempering designations that distinguish how the thing is heat treated. And the heat treatment can substantially change the properties. Yeah, I didn't write any of these down. So there's a table 11.3 on page 357. So T6 is the one that I'm, 6061 T6. What page is that? It's a very common one. 357. Magnum. So there's no song that goes with that though. So anyway, so the designations that you're going to be most interested in are O, which is fully annealed, so that there basically is no heat treatment. And then recognizing that H and T with some number after them, are the 2 broad categories. H is hardened, and T is tempered. Okay. So H is hard, strain hardened. In other words, it's been shot beamed or stretched or beat on or whatever to strain harden it. We talked about that before. Moving further up the curve. And then T is the tempering, and then there's some kind of number that would go with that. And you'll get on the table. Okay? Any questions? Okay. The rest of these I'm just going to go through. Magnesium is an HCP material. So it has an even lower density than aluminum. 1.74 versus aluminum's 2.7. So it's an even lighter weight material. And that density is the lowest of all the structural materials. So it's more of an aerospace application, obviously. Low density.
What's its strength relative to aluminum?
I don't know. I don't deal much with aerospace structures. So, but magnesium is, and it's more expensive, substantially more expensive.
Magnesium, just elemental magnesium? Or
Magnesium-based alloys. So yeah, you probably wouldn't use elemental magnesium. You'd use some kind of alloy. The expensive aluminum. There are some expensive aluminums, but the expense comes from this primarily, from the tempering process. Although, you know, it's also, you know, obviously what you put in it matters some.
So how do you get some aluminum with really high melting points? Does that just have to do with how you dope it?
With really high melting points.
Because normally aluminum has relatively low melting point, like aluminum foil, but like there's aluminum used in aircraft that is much higher melting point, right?
Yeah, but not that much higher. You can't, you're not changing the melting point that much, no. In fact, typically as you alloy things,
Yeah.
right, the initial, if you just put a little bit of something else in there, it typically lowers the melting point, unless you're doing it as a solid solution. Right, you notice all of our curves, right after the melting point of the pure material, the curve went down. The exception is the full solid solution, where it actually went up for one side. All right, next, titanium. That's also an HCP, hexagonal closed path. The density of titanium is between that of aluminum and steel. So it's an intermediate, but it has a much higher, it has better high temperature strength. Because it's HCP, it has fewer slip systems, fewer active slip systems. And it also has corrosion resistance and passivity that rivals aluminum. Titanium doesn't corrode very well, certainly not nearly like steel does.
What's passivity?
Passivity? The same thing I talked about with aluminum, that it forms an oxide layer that then the stuff can't get, oxygen can't get through. So it's called passivating. It makes the corrosion process passive. Does that make sense? Okay, so titanium passivates the same way aluminum does. I think actually titanium's passive layer is thicker than aluminum's. I think it takes more corrosion, but I don't remember that for sure. So again, primarily used for high temperature applications. That's where titanium is most useful. Copper, again, it's an FCC material. Where do we use copper?
Wires.
Right. What do we use it for? What
Pipes.
property?
Conduction.
Conduction, both thermal and electrical conductivity, right? Because they're both related to the motion of the electrons. So the main reason we want that is high conductivity. Although not the highest, does not have the highest conductivity.
Silver?
Silver is actually higher conductivity than copper. Right, so when you're trying to couple your heat sink to your processor, use silver paste, not copper paste. So silver has a slightly higher conductivity. When we alloy copper with zinc, what do we call it? Brass.
Crayons.
And anything with tin, silicon, aluminum, oh man, aluminum, or even nickel. What do we call those? Mix it with tin, silicon, aluminum, or nickel, and copper. What do we get?
Is that bronze?
Brass.
That's bronze.
Yeah.
Ooh, so bronze is a very broad spectrum.
Yeah.
Very bronze.
And then we use bronze as bronze has a higher strength than brass does. Copper is fairly soft. By alloying it with zinc, it improves its strength. That's what we make brass doorknobs, right? Things that are, and this is a substitutional solid solution. But then we mix in, and nickel is too, right? We did the copper nickel phase diagram. But bronze is higher strength than brass does.
Is brass,
So we didn't have the brass age, we had the bronze age.
is that real cheap?
What's that?
So is brass pretty cheap? material make it?
So make it
Cheap?
so-
Zinc is cheaper than copper. But
So
nickel,
what about brass makes it like, why would somebody use that over another material like bronze?
it is cheaper, so brass is cheaper. You know, nickel's more expensive than zinc, right? And brass is fairly good at corrosion resistance. I mean, it's not, it corrodes, right? You see antique brass, but it's just a brown film. It's not like a runaway corrosion like iron can get.
Isn't bronze like the same kind of thing?
Patina, the same kind of patina. Is that what you mean?
Confuse Blake with your words.
Sorry, the patina, so like the green copper, like a copper roof turns green, they call it, it's patina.
Okay.
Okay, so, yes, so brass has just a dull brown patina, it doesn't, you know. Although I think if you let it go long enough, it'll turn green too.
What's bronze's patina?
It's different for the different element, I don't know. Bronze is more red than brass, but I think that also depends on which alloying element you're using to make the bronze. Okay, oh, I'm out of time. The last two I want to get down were nickel. You might actually encounter some of these mono, Inconel, and Hasselboy.
Now you're just making up words.
I think Hasselboy is an E. I have it as an E. These two are super alloys. Again, the really high temperatures, high strength at very high temperatures. Monel is what you call 70 nickel, 30 copper. The rest of these have nickel, chromium, iron, molybdenum. There's several of these, several alloying elements there. And the last one that's important is zinc. And we use zinc as a standalone material for galvanization. I talked earlier about, you know, you have galvanized steel, or galvanized nails that you might use on a deck, or a galvanized trash can. I talked earlier about the facets you can kind of see on them, right? The purpose for galvanization relates to zinc's corrosion properties. There's a whole list of metals in terms of their activity, and you always want whichever one. There's a. We're not going to have time to go into this, but the bottom line is you have two metals on the list that are in contact. The one on the top is going to corrode away, and the one on the bottom, or it depends on which one the list is, which way you list it. But the point is, there's just an inherent difference in the galvanic character of each metal. And so if I put steel and zinc in contact and stick it in a bucket of salt water, the zinc will act as the dissolving, I can't remember, the oxide, no, I'm trying to figure anode and cathode. I always get those mixed up. But anyway, the anode, zinc will act as the anode.
Mm-hmm.
So it'll dissolve and leave the steel unrusted. Does that make sense? So you form a little galvanic cell, basically form a little kind of a little battery, and the zinc dissolves in deference to the steel. And so zinc is used for galvanization so that if you have a scratch in your garbage can, right, so that the steel is exposed, it won't corrode that scratch because instead the zinc around the scratch will dissolve and sacrifice itself for the steel underneath. In fact, back in the day, they used to actually screw or bolt zinc ingots on the bottom of a ship to keep the ship from corroding as sacrificial anodes. So as it's sailing through the water, it would have the zinc dissolving and the steel would stay uncorroded.
That's in here somewhere.
I'm sure that's very environmentally friendly.
You know, stuff they did in the 1800s wasn't typically done for environmental friendliness. All right, next time ceramics.